What's up, everybody? In this video, I would like to show you how to graph data to a linear fit. That is, figure out how to plot some data so that you get a straight line, and then interpret the slope of that line to gain some experimental value of a constant. Basically, what I'm saying is, the premise is this. You'll be presented with a table of data in some scenario. You have to figure out what to plot on the y-axis, on the x-axis, so that 1, you get a straight line, and 2, that you could interpret the slope of that line and y-intercept to determine relevant constants in the problem. So for this one, the example is you've repeatedly thrown a mass upward with the same initial speed from the tops of cliffs of varying height. So there's some cliff height here, you're standing on the top of this thing, you go some distance h up, some distance h, you measure that cliff height, you go stand on top, and you throw an object up. You're always going to throw it up with the same initial speed. So this initial speed's always the same, but then obviously the speed it has when it gets down to the very bottom, right before it hits the ground, these are going to be different, and you measure those final speeds. So these final speeds are the speeds right before you hit the ground. These heights are the heights of the cliff. I guess these aren't much of a cliff, 1 meter. I'm not sure if that qualifies as a cliff, more as like a small step, a boulder or something. But you're standing on different heights. You're always shooting them with the same initial speed. You measure the final speed right before it hits and the height of the cliff you threw it from, keeping this initial speed constant. You took your data, you throw it from a height of 1 meter with that initial speed, and it goes pretty fast when it hits the ground. And the higher you throw it from, obviously, the faster it's going to be going right before it strikes the ground. Here's your data. The problem is if we just naively plot, say, speed here, the final speed v, and the height here, we are not necessarily going to get a straight line. Our data might be like a square root or something like that, or it might be like a parabola. It might end up looking like that. We want to figure out how to graph this data so that we get something that looks like a straight line. So the first step to do this is to just figure out what equation relates all this data. So what is the equation that relates all this data together? Well, we've got final speed v, we've got height h. I know my acceleration should, so the goal here eventually is going to be to get an experimental value for the acceleration. My acceleration should be negative g, and my initial speed is constant, always the same. So time is left out of this entirely. These are all going to take different amounts of time, but I don't know what time it's going to take, so I want to use the formula that's got no time in it. So I'm going to come down here, and I'm going to say that v final squared should equal v initial squared. This is the one that has no time in it, plus 2a. A is, we know it's going to be negative g, it's a freely flying object, times delta y. Let's see, we started up here, or at least our object did. The mass ended down here, it ended up below where it started. That displacement, that delta y, is going to be negative h. So it's going to be negative whatever this height is. So if I simplify this a little bit, I can just say that this is going to be v final squared equals v initial squared, and then the negatives cancel. I just get plus 2 times the acceleration due to gravity times the height of the cliff that I threw it off of. This is the equation that relates all our data in a way that lets us find what we want to find. So the next step is going to be to figure out, let me move this down, see if this stuff moves with it. Oh, not that stuff. Just kidding. Move this stuff down here. What could we plot on the vertical and horizontal axes in order to get a linear fit? So in other words, how could we plot this data so that we get something that looks like a straight line? So what we could do is, we've now got this here. This is our equation. We need to put this in the form of a straight line. So what I do is I look on the left. My y has to be something that changes. My x has to be something that changes, and my slope has to be something that's constant. Otherwise, I wouldn't get a straight line. Think about it. You'd get something with changing slope, and that's not a straight line. So my slope has to be some constant in the problem. Y has to be changing. I'm looking over here. This v squared is all the way on the left. This y is all the way on the left. I could call v squared my y. So y could be v squared. I've got to do v squared. I can't just do v. If I try to plot v here, again, I'm not going to get a straight line. I'd be plotting like y squared equals all this mess. But if I just call y v squared and plot those data points, Now I'm going to get a straight line. My x, let's see, I can't make x v naught squared. This is the same every time. This is not changing. This cannot be x. X has to be something that's changing. There has to be different data points for x. The only other thing that was changing was h. So h here could be my x. And that means the slope is always everything multiplying the thing you called x. So we called hx. That means 2 times g would be my slope. My slope's going to represent 2 times the magnitude of the acceleration due to gravity. And I do have a y-intercept. This b would have to be this v initial squared. So this is going to be the y-intercept for this problem. So that's a fine interpretation. You can plot v squared on the vertical, h on the horizontal, find your slope, you'd get it equal to 2g, and then your y-intercept would be the initial speed squared. There's other ways to do it if you wanted to. You could associate, oh, it's going to erase black? That's not good. I need to erase white. Shoot, hold on a second. Maybe I could do this. All right, well, I didn't want to erase anyway. Screw it. Okay, you could not put the 2 here. You could be like, screw that. Take the 2 out. Don't include the 2 here, but include it here. That's fine. You could plot 2h on your x-axis. It's just your slope would now represent g. I'm not going to do that. I'm not going to do that because I'd have to make another table to find all the 2h's. I don't want to bother with that. So what I'm going to do now is I have to find what v squared is. So I come up here, and I'm going to be like, all right, v squared. I'm going to erase this mess over here, get rid of this. So I need to make a new column. I'm going to be like v squared. What the heck is v squared? V squared is, well, at 1 meter it was 6.7 squared. So you really have to actually square these. 6.7 squared is like 44, about 44.9. 8 squared is going to be 64. 9.1 squared comes out to about like 82.8. 10.2 squared is 104.04, and 11.1 squared is 123.21. Those are my speeds squared. So I come over to here and I say, all right, I got to plot these. Remember, v squared is my horizontal, or sorry, v squared is my vertical axis. So I come over to here and I say that this is going to be v squared, and it's going to have units of meters squared per second squared. Oops, because it's a squared speed. And then this is my h, and that's going to have units of meters. I pick a good choice for my divisions here so that I fill up most of the chart. I got 1, 2, 3, 4, 5 for h, so that's easy. 1, 2, 3, 4, 5. Remember, I'm not plotting speed final. I'm plotting final speed squared. So I come over to here. I'm going from 44, about 45 to 120. So I guess I could do, let's see. I could do 30, 60. Yeah, that's going to work. I could do 30, 60, 90, 120, and then I guess I wasted a little space up here. It's all right, 150. All right, that's one choice. You could choose it in a way that might make more sense. Let's just see here. So at 1 meter, it should be 44.9. Let's say the way these divisions are, that would be 45. Oh, so that's almost exactly right here. That worked out nice for me. Boom, that's one data point. 2 meters, 64, so 2 meters, 64, that's gonna be like right around here. 3 meters is 82.8. I'm looking at 3 meters is 82.8. 82.8. Oh, my Mac is about to go to sleep. What a loser. Let me plug it in. Okay, so 82.8, 3 meters is going to be right around here-ish. 4 meters is 104. That's going to be right around, let's see, this would be halfway in between. 30 would be like 105, would be right around here-ish. And then 5, oops, no, actually, halfway between 90 and 120 should be almost exactly this right here. It's pretty good. And then 5 would be 123. That's going to be right around there. All right, we plotted our data. Notice we did get a straight line. If I tried to do V versus H, I would not have gotten something that looks nice and linear like this. This is why we do it. Now I'm going to draw a best fit line through here. Your best fit line should have as many above as it does below. You don't just get to connect initial and final points. I'm not allowed to just do this and be like, I'm done. Even though that worked pretty well here, what I want to make sure of is that I go with as many points above this line as there are below. That looks something like this. So I've got about 2 points below, about 3 points above, roughly. That's a pretty good best fit line. Do not just connect the first and last point. And draw nice and big so that it crosses over here. It's important that it crosses over here because you're going to use that to figure something out sometimes. So that's our data, that's our best fit line. What's next on this worksheet? It says to pick 2 points on your best fit line and find the slope. So we got to find the slope, and you do that the way you always find the slope. You pick 2 points, but pick 2 points on your line. People want to pick 2 points from their data table. They're like, I'll pick these 2 points and these 2 points. You're not allowed to do that. Don't pick points from your data table at all now. Now that you have your line, pretend like this doesn't exist over here. So we've got our line, pretend like that doesn't exist. Pick 2 data points that line up perfect. Look at this one. That's a beauty right there. Crosses exactly at the hash mark. Which other one is good? Ooh, man, this is gorgeous right there. Okay, circle them too, so that I know you know what you're doing, you know what you're doing, and the grader on the AP will know what you're doing. We're going to find the slope. The slope is always rise over run. So it's y2 minus y1 over x2 minus x1, except here y2 is really like v squared. So we take this point over here, and I just go to the left, and I say that that was exactly between 120 and 150, and that means halfway between 30. So this is like 135 minus, I go to this point here. I guess each division here is 7.5 because it's 30 divided by 4 is like 7.5. So this is a 7.5 less than 60 is going to be like 52.5 is my y1. And then I do my x2 is going to be right there. That's going to be 5.5 minus, and I'm leaving units off here, but we'll clean that up in a second, minus 1.5. And what I get out of that, if I just take all that, and take 135 minus 52.5, and I divide that by 5.5 minus 1.5, I'm getting 20.6. So what I get out of this is 20.6. I could check my units. The top was meters squared per second squared, because that's what this unit is there. The bottom one is meters. So when I take that and divide by that, what I'm going to get is meters per second squared, and that's good. That's an acceleration. And when I look down at what this stuff was supposed to represent, remember my acceleration, or at least my slope. My slope here was supposed to represent 2 times g, 2 times an acceleration. So it's good that I got units of acceleration. So my slope is equal to this number here. This 20.6, that's what my slope is equal to. What do I do with it? Well, now that I know that, I can come down here, use the value of your slope to find the acceleration due to gravity. So this is not the acceleration due to gravity. Remember, our slope is 2 times g. So at this point, you simply say that this is your slope. This is the number for my slope. That is m. What is m? Well, m we just said was 2 times g. So m equals 2 times g. In other words, 20.6 is your slope. I'm leaving units off. 2 times g. So our experimental value for g would be 20.6 divided by 2 is going to be 10.3 meters per second squared. Not the best experiment ever, but that's pretty close. That's not really a bad percent off. The actual value is 9.8 or 9.81. So we got pretty close. On the AP, this would be like, they'd be like, high five, dude, you did it, wonderful. We keep going. What else can we do with this? That's usually one thing you do. So one of the big things you do is just find the slope and interpret it. And that's what we did here. So that was the goal of this, is to get an experimental value for g. That's why you're doing it this way. And if we keep going, we could do more, because it says, what would the y-intercept represent? We do have a y-intercept. Look at our y-intercept represents the initial speed squared. So if I come over to here to my graph, and I just ask, well, what was the y-intercept? That would be this point here. and it's crossing almost exactly at 22.5, since each of these divisions is about 7.5, because 30 divided by 4 is about 7.5. 22.5 represents what? It represents v naught squared. So we can get the last question down at the bottom. Says, what's the initial speed? Well, this is equal to v naught squared, because that is the y-intercept. That's the b. B is that. So if I just take a square root of both sides, I get that v naught would be 22.5. Square root is about 4.7. So we even got an experimental value for the initial velocity of the object, 4.7 meters per second. That was the goal, is to use your slope and y-intercept. Sometimes it'll just be the slope. Sometimes it'll just be the y-intercept. Sometimes a problem would ask you both, and you'll need to deal with both of these. But the idea is to use the slope and the y-intercept to gather some experimental value for some constants in the problem. Those constants in this case were the acceleration due to gravity and the initial speed you threw the object. Now you might be wondering, like, why in God's name would you choose to analyze data this way? I find a lot of people want to just say this. They go to their initial table and they're like, dude, you want an acceleration due to gravity? I've got a kinematic formula. It's just v squared equals v initial squared plus 2 times negative g, negative h, so those negatives go away. I just got this. I've got an h. Why don't I just take 1, plug it into there, take 6.7, plug it into there, and then you're like, oh crap, wait, I don't know the initial velocity. So that wouldn't work here. Because we didn't know the initial velocity, wouldn't necessarily help us. In order to get that, we'd have to know g. And in order to get the g, we'd have to know v initial. So this technique is a little more powerful than just like finding values from all of these and averaging them. I find students want to do that. They want to find a g from this, find a g from this, find a g from this by plugging into a formula, and then just averaging all the g's. That's okay. It'll give you a value that's basically close to the value you got through this technique. So if all you wanted was g and you were able to do it that way, not that bad. The reason this technique is superior is, for one, we couldn't do that here because we didn't know v naught. So you had to use it in this case. But even if you couldn't, even if you didn't need a v naught, say you dropped it from the top of the cliff, so these were all 0. This technique is still nice because just looking at your data, look at our data here. It fell along a straight line really nice. We know that, all right, this was a pretty precise experiment. According to kinematics and freely falling objects, this should have, based on how we plot it, give us a straight line, and it did. If it had given us data that was like here, and then up here, and up here around the line, even when we have a reasonable scale, we haven't zoomed in too close. If it gave us some scattered mess, we'd know, ooh, our experiment screwed up. Something bad happened. And you don't necessarily get that visual recognition from just a table. If I just look at a table of numbers, it's hard to tell, hey, was this precise or not? I don't know, they're just random numbers. But if you plot it, you can visually just see, these all are fitting along my line really well. I know this experiment was probably pretty precise. Or if you don't know the relationship between the variables, you can plot them and just see, okay, there's a linear relationship between speed squared and h. Or if this didn't give you a straight line, you would know, all right, my relationship must be something different. So if you're trying to figure out the relationship in the first place, this is also a technique you could use by plotting the data and just seeing what it looks like, and then trying to plot it in a way that gives you a linear fit. If you can figure that out, it gives you a way to figure out what is the formula that relates the variables. So recapping, if you're given a data table, you can figure out what equation relates to the data. Given that equation, you can figure out what you can plot as a y, what you can plot as an x. That lets you interpret the slope as whatever's multiplying this thing that you called the x-axis. Also, the y-intercept would give you whatever plus b term there was in your formula. And this is on the AP a lot. It's definitely going to be on my test a lot. You're going to have to know how to do this. It's confusing at first, so it takes practice. Got to practice, got to do it on your own. One more thing before I let you go. You didn't have to make v squared the y. You could have chosen to make, say, like v the y. You just have to take a square root of this whole equation. If you took a square root of this whole equation, ooh, that'd be a mess. It's not a good thing to do because this v squared is going to be under the radical. Let me put it this way. You could have moved h onto the y-axis, v squared onto the x-axis. If you did that, if I solve for h, I could say that h is going to be let's see, what is it going to be? It's going to be v squared over 2g. If I divide both sides by 2g, and then I'm going to move the v naught over, minus v naught squared over 2g. You could try it this way. H would be the y, v squared would be the x, the slope would be 1 over 2g in that case, would be what the slope would represent. Problem is, now your y-intercept has v naught and g in it. It's not that big of a problem. You can still do it this way. You can plot h on the y, v squared on the x. Whatever's multiplying v squared, in this case 1 over 2g, is multiplying your x. That would be your slope. You could find your slope, then you can solve for g. Once you have that g, you could bring it over to here and interpret that with your y-intercept, your new y-intercept. All the numbers would be different, except for the h. Your h and v squared would just be on opposite sides. You'd get a slope that's 1 over what you got before. Your numbers should come out the same. They would look different on here. The like scales would look different. And then you'd have to use that g over here to then interpret what your v naught squared is. What I'm trying to say is there's different ways of analyzing the data that are correct, but there are more ways to do it incorrectly. So you got to pick a correct one and go with it. And if you do that, you can interpret the slope, get an experimental value for your g, and in this case, get an experimental value for your initial velocity.